In this video, we're going to look at how to solve compound inequalities. When we say compound inequalities, we mean we have more than one, which is 2 or 3 or 4 inequalities. In these two examples I'm going to give you, we will only talk about 2 inequalities. So there are 2 types. The first type is, say we have 3x minus 2 greater than or equal to 1, or negative 2x plus 4 less than or equal to say negative 3. Alright, so here we have the 2 inequalities, as you can see, which are joined by the word or. So the first one, 3x minus 2 greater than or equal to 1, we can solve each one as we like we solve equations, but paying attention to the sign change when we divide or multiply both sides by a negative number. So the goal is the same as solving an equation. We want to get the variable x by itself. In order to do that, we have to add it to both sides to get rid of that minus 2 there. So we have 3x greater than or equal to positive 3. Now we can divide both sides by 3. So we end up with x greater than or equal to 1. So that's the first inequality. Now the second inequality, we're going to solve it to get x by itself. So we subtract 4 from both sides. So we have negative 2x less than or equal to negative 7, because negative 3 minus 4 is negative 7. Now we need to divide both sides by a negative number, which is negative 2. And when we do that, we have to remember to flip the sign. So less than or equal to will become greater than or equal to. Now negative 2 divided by negative 2, they cancel. We get a 1, but 1x is still just x. Greater than or equal to negative divided by negative, we get a positive. And 7 divided by 2, we can leave it as it is. It's a reduced fraction. And we're going to bring down that word or. So when we have 2 inequalities, or even 3, you will just have to solve each one separately. And then we can put the answers together. So now we look at the graph for this question. So we have x is greater than or equal to 1 right here. If it's equal to, we're going to make it a closed circle. And 7/2 would be 3.5, so which it should be on the right side of 1 because it's bigger than 1. So now we have the solution of the first one, which says x should be a number bigger than 1 or at least equal to 1. So that means x has to go to, we got to shade the numbers on the right side of 1. So all of these numbers here. And x is greater than or equal to 7/2. So that means we're going to start from here and still go to the right. As you can see, because the word is or means one or the other. So the numbers can either be here, all of these, or these numbers. As you can see, these numbers are already included in the solution of the first one. So that will give us all the solutions. So it's either here or there, as we can see from the graph. The numbers, let me use a different color to show those numbers. So these numbers are greater than 1. So they're certainly solutions of the first inequality, which will also be the solution of the whole compound inequality, because it says or means the solutions of the first one or the solutions of the second one will be the solution of the whole compound inequality. So these numbers are greater than are greater than 1, so which are solutions of the first inequality, which should be the solution of the compound inequality. And these numbers are greater than or equal to 7/2. They're not only greater than 1, but also greater than 7/2. They are actually solutions of both. Of course, they should be the solution of the original compound inequality. So now we can see this, the numbers we shaded or highlighted will be all of these numbers starting from 1. So now we can use interim notation to describe these numbers. So we start from the left-hand side, the smallest number possible, which is 1. Because we want to include 1, we're going to put a square bracket right next to, on the side of 1. And then we put a comma. And notice all the numbers continuing to the right forever. These are all the solutions. There's not really end. So as we know that we can use positive infinity to describe the sort of the end of the biggest number. Okay, so that's the how we solve the first inequality. As you can see, we have 2 inequalities. Now, in the second one, some inequalities actually can be put together into like looks like a single combined inequality. So let's do another example. -2 less than or equal to 5x minus 7 less than or equal to well, we don't always have to have equal to. So the equal sign, you could have one of them with the equal sign, the other does not, or you could have neither of them with the equal sign. So I'm just going to make one side with the equal sign, the other side without an equal sign. Let's say 6. Okay, so this looks like a single one, but notice that we still have 2 inequalities here. They're not separated as in the first case, first example. There's a less than or equal to here, and there's another less than sign here, and it's really 2. It looks like one expression, but there are really 2 inequalities here. If we can separate them if we want. So here this is what we can do to separate them into 2, as we have seen in example 1. So what we can do is we can bring down the first inequality sign less than or equal to, and bring down the left hand side, which is -2, and bring down the right hand side, that's 5x minus 7, and we got our first inequality. And similarly, we can bring down our second inequality sign, which is a less than sign, and bring down the left hand side, that is 5x minus 7, and bring down the right hand side, that's a 6. And the word we're going to be using is and. The reason we use and instead of or is because 5x minus 7 is between -2 and 6. The word we use is and, which means this 5x minus 7 has to be satisfying 2 conditions, not one of them, not one or the other. So both of, not only it has to be less than 6, but also it has to be greater than or equal to -2. So now we got a problem very similar to example 1. We can solve it by getting x by itself. Notice that the variable x is right here. So we want to get rid of that -7 first. We add 7 to both sides. And then we can divide both sides by 5. Now we got 1 less than or equal to x. And now we can solve the second one by doing exactly the same thing, because we still want to get rid of that -7. We still want to add 7 to both sides. And then we are going to get rid of 5, so we divide both sides by 5. Exactly, as you can see, we're doing exactly the same steps here. The steps we did, adding 7 to both sides to get rid of that -7, same thing here. And dividing both sides by 5 to get rid of that 5, same thing here. And the reason is because they share the the same expression, 5x minus 7, 5x minus 7. So if you want to get x by itself, of course, you're going to do exactly the same thing. So when you get down here, when you bring down that word joining them, so we got 1 is less than or equal to x, which means x is greater than or equal to 1. So let's draw a graph to put the solutions here. So there's one number which is 1. The other is 13 over 5. Apparently this is 2 and 3/5. That is bigger than 1. That should go on the right hand side. So make sure when you put numbers here, do a comparison. Make sure you put the big numbers on the right, smaller numbers on the left. Now let's draw the graph. One thing we got to be careful is, although we see a less than or equal to, we're not going to go to the left because we're trying to draw numbers for, highlight those numbers for x. What kind of numbers are for x, are the values for x? Now read this, translate this into English sentence. It says x is greater than or equal to 1. We know that alligator's mouth is going to eat the bigger one, which means x is bigger. If x is bigger than 1, then the numbers for x should be on the right side of 1. Again, we're drawing the graph for x. So these are going to be the numbers for x. Although we see a less than sign, we're not going to go to the smaller numbers than 1 because x actually is greater than 1. The reason is x is on the right hand side. So if you rewrite it, you actually can get x greater than or equal to 1. You know, alligator's mouth eats the bigger one. And so these two are equivalent here. So that tells us x should go to the right. So that's the solution for the first inequality. Now we're going to draw the solution for the second one. That's x is smaller than 13 over 5. Because this time we don't have an equal sign, I'm going to have to draw an open circle to dig that number out. And then x is smaller than 13/5. That means we got to go to the left side of 13/5. Now, notice the keyword is and, not like the first case or you take one or the other. If the number is a solution of one of them, then it should be the solution of the whole compound inequality. But and is not the other. And it means you have to have both. So we have to look for the numbers that are not only greater than 1, but also less than 13/5. So let's look. These numbers are greater than 1, greater than 1, greater than 1, up to this point. If I keep moving across 13/5, these numbers are still greater than 1, but they are not going to be satisfy the second inequality, less than 13/5. They're going to be bigger than 13/5. And notice and means we have to look for numbers to meet both requirements. So that's why we have to stop right here. So the solutions will be numbers from 1, including 1, all the way up to 13/5, but not including 13/5. And so let's double check. Do these numbers in red meet both requirements? And they do, because they are on the right side of 1, which means they are greater than 1. And they are also on the left side of 13/5, which means they are smaller than 13/5. So they meet both requirements. So these two examples are different. In the first example, it just says or. Or means you don't have to meet both requirements. If you meet one of the requirements, you are good. And that's why we can see those numbers right here. Let me use a different color. These numbers right here are still solutions. Although these numbers are not greater than 7/2, they're not greater than 7/2, they are still solutions because they are greater than 1. So you don't, again, you don't have to meet both requirements. These numbers meet the first requirement, then they should be solutions. And these numbers, they meet both requirements. They are more than qualified. Okay, so that's the difference.